All right, so today we're going to be talking about objectives 8, 7, 9, and 10. And what the purpose of this is to apply the properties of intermolecular forces. And what is the purpose? What are we going to actually be doing is describe what happens during dissolving and predict the solubility of compounds. So quick little recap. When you make a solution, right? A solution is a mixture, all right, where everything blends together smoothly. Something gets dissolved called the solute, and that's present at a lower percentage, and something called the solvent does the dissolving, that's present at the higher percentage. So question number 1, quick little recap. If you're making Kool-Aid, all right, which one is the solute? All right, so hopefully you chose A, that the powder is the solute because it's present at a lower percentage. All right, so which one is going to be the solvent? And hopefully you answered that B is the solvent. Water is present at the higher percentage, all right, when that solution is made. So what is dissolving anyway? All right, so here's an example of NaCl in water. All right, we know salt is an ionic compound. So here's the salt when you first put it in. All right, and what you'll notice is eventually there will be less and less salt. So what's actually happening? All right, this crystal here, right, is representing the salt, all the NaCl's. All right. Over time, all right, these here are the waters. Those are the H2Os. Over time, all right, these H2Os, these water molecules, are going to start surrounding each ion. All right, so these water molecules go over to NaCl and start breaking it up so that instead of it being NaCl together, you have Na and Cl, they're all separate. And now it's basically like the ions are sort of hiding behind these water molecules, or the water molecules have surrounded it. So here is kind of a bigger picture. What you'll notice is these are waters here, all right? The blue is represented by the H, and the red is represented by the O, all right? So you can see that this oxygen is partially negative. And see how this red side is all around the Na? We know opposites attract. On this side, the blue, the hydrogen side, is all around the Cl. So when something dissolves, water molecules surround the ions. All right, so question 3, here's a little recap. All right, so based on that picture we just saw, the water molecules are the one that are surrounding each ion individually. So that's C. All right, we know that the ionic compound actually breaks apart and the water molecules start to surround. All right, and it's not D. So we just talked about salt and water, right? You know, if you put sugar in water or Kool-Aid water and dissolve. But there are times when substances don't dissolve in water. Why don't they mix together? So if you put oil in water, right, you mix it in, you shake it up, it might get bubbly, but it'll separate. Now, one of the things we've talked about in the past is density. Yes, density is one reason why they won't mix, but it's not the only reason. It's not like the underlying cause. So in order to mix successfully, the solute and the solvent must be able to interact, all right? And this is where those intermolecular forces come in, right? Polar substances, right, like water, all right? Water has polar bonds, all right, where the oxygen has a higher electronegativity, all right? And so we say that that has a dipole moment. Polar substances will interact with other substances that are polar or have a dipole or have a charge, right? So if you think about oil, oil must not have a charge, right? So it's made of many carbon and hydrogen atoms bonded together. So an example of a possible oil chemical formula, C8H32O2. Now what we've talked about is CH bonds are non-polar, right? They don't have unequal sharing. They're very equal, just like if it was carbon bonded to carbon or hydrogen bonded to hydrogen. So because oil is non-polar, right, but water is polar, they don't interact. so that water doesn't surround those oil molecules. They basically stay in their separate places. In contrast, opposite of NaCl, right? NaCl has that positive and negative ion, and then water has that positive and negative side, so they do interact, and as we saw a few slides ago, those water molecules surrounded each of those ions. So this has to do with the notes in 8.9, and this would be something pretty important to write down somewhere, all right, or to explain in your notes 8.9. A few weeks ago, we actually talked about 8.12, where we could, look at a table and say, hey, Na is always soluble, NH4 is always soluble, but OH generally not soluble. How can we predict a solubility without having that? All right, and what if we have other solvents? All right, so there's this phrase, likes dissolve likes. And what that just basically means is if something is polar, it's going to interact with other polar things. They're alike. Right? The word miscible is what we use when we talk about liquids mixing. Usually it's a solute and solvent dissolve. When it's a solid into a liquid, we say dissolving. When it's two liquids, we say miscible. So if you have a nonpolar solute, it will dissolve in a nonpolar solvent because these are likes. If you have a polar solute, it will dissolve in a polar solvent, all right, because those would be likes. Now, ionic compounds have a charge, all right, so they typically do dissolve in water, right, like polar solvents, because they have an ion or a charge. So let's take a look at a couple examples. We have sodium iodide and we have water. Now I know that NaI is ionic. Sodium is a metal, iodine's a nonmetal, so it's ionic. And water is polar. So what we just said is ionic solutes do dissolve in polar. So yes, it's going to form a solution. And our explanation is that they're likes. Ionic will dissolve in a polar solvent. Now, if you take future levels of chemistry, likes dissolve likes, you'll need to go a little more detail and say the charges of an ionic compound interact with the polar parts or the dipoles in water, right? But right now we can just use this as our example. So the next one we have is HCl, right? So we have hydrogen and chlorine. They're both nonmetals, but if you look, they're really far apart on the periodic table, all right? So that would be a polar solute, that should say P, and oil, all right? We just talked about oil being nonpolar. So here you have something that's polar and something that's nonpolar, right? Those are not going to form a solution because they are not likes, all right? It's a polar solute, but it's a nonpolar solvent. All right, we'll do one more example together. Here we have CH4, carbon and hydrogen, carbon and hydrogen. Those are going to be nonpolar because C's and H's are nonpolar. Sorry about those lines. Oil is also nonpolar. All right, so if you have two nonpolar things, they are going to form a solution because they are alike. They're nonpolar, their LDF or induced dipoles will interact with each other. All right, so now I've got these three in a box. Which combinations in the red box will mix or dissolve and form a solution? Go ahead and answer that now. All right, so KBr is ionic and oil is polar, so that would be a no. CH4 is nonpolar, water is polar, so that would also be a no. And then HF, all right, H and F, those are both non-metals, covalent compound, but very polar, and water is polar, so that's a yes. All right, so only HF and water will form a solution. So let's say you need to wash off grease, all right? What you would use is use soap. Why would you use soap? All right, so here's a simple diagram of a soap molecule. Soap molecule has two parts. It's got this polar part, right? We call that the polar head. And then it's got this non-polar part. That's a tail, all right? This polar part is attracted to water, and this nonpolar part is attracted to fat or grease or oil. Okay? So if you look at this little picture here, it shows the tail end surrounding this oil particle, and this, charged end, the polar head, is near the water. So you wash your hands, the soap will surround those oil particles, but then when you rinse it off, it will go away and hopefully leave your hands. So a little current events application before you answer this question is how soap works in terms of the coronavirus. So here's another diagram showing the hydrophilic head, which is attracted to water. Hydrophilic just means water-loving. And here's water. And then you have the hydrophobic tail, right, which is attracted to fat, oil, all those nonpolar things. Right? Viruses have a fatty lipid membrane. The membrane is the outside, right? Those of you in biomedical may have heard some of these words before. Think back to earlier biology classes, right? If you add soap and water to this, right, the soap is going to bond to the fatty lipid membrane, the outside, right? But then you add water, all right? And that's why it's important to actually scrub and wash your hands so that you can do this mechanical separation here, all right? And get everywhere. And then the soap will bond to the water, all right? You rinse it off. The push and pull, right, is breaking things apart. And then you rinse it off, and there you have it. All right, so question 5 is, how does soap work? All right, hopefully you saw the right answer here. If you read the other ones, it doesn't destroy matter, right? Matter cannot be created nor destroyed. Universal solvent, that's water. And then we haven't even really talked about acids and bases. Last thing, we're just going to talk quickly about the gaseous state of matter. So, can gases dissolve? The answer is yes. If you see here, there's kind of either a bottle of seltzer or, Sprite or something like that. When soda is created, it involves carbon dioxide being dissolved in water. All right, so how can you get a gas to dissolve in water? One thing you'll notice, all right, I lost my axis here, but that should have said solubility, is by increasing the partial pressure. All right, we haven't talked too much about pressure in some of our classes yet, but the idea is as pressure increases, solubility will increase. Those are a direct relationship. All right, for gases, all right, as temperature increases, solubility will actually decrease. So you'll notice, right, that over here, these gases are more soluble at lower temperatures. All right, here, this is at a higher pressure. All right, so here's talking about carbonated soft drinks. All right, real life tip, if you are tired of your soda going flat and you have it in a bottle, right, you don't want to just take off the cap and leave it open. No, what you want to do is you want to make sure that cap is on tight so that no pressure can escape. But if you want to make it so that it's even a higher amount of pressure, if you squeeze the bottle before putting the cap on, so there's not as much space here, that will help create a high pressure and help keep your carbon dioxide dissolved. All right, so the last question here is, when is a gas most soluble? And I had already given you answers, so hopefully you have at high pressure and low temperature. Have a great day.